So far, we have gone through the working of center-tapped full-wave rectifier. Let us have a look at some questions asked in the previous GATE exams along with some expected questions from this particular topic. The first question. In the circuit of the figure, assume that the diodes are ideal and an average indicating voltmeter is connected across the load resistor. The voltmeter will read. So there is a load resistor RL, R instead of RL. We have been practicing like RL. Okay, it is R. They have not mentioned anything. We can take RL. Doesn't matter. RL, and an average indicating meter is connected. Average indicating meter means it is just nothing but a DC meter, which gives VEC, average value of the output voltage. What is the formula for VDC? We know VDC is equal to 2 into output peak amplitude by pi into RL by RS plus RF plus RL. Here the diodes are ideal. Diode forward resistance is 0. They didn't mention anything about the transformer. We take ideal case, that is coil's internal resistance is 0. If that is the case, removing this part, RL cancel, and it is equal to 2 into peak amplitude of the input by pi. We can write it. So what is the peak amplitude of the input voltage? You see, here in the problem, it is mentioned 230 volts, means it is the RMS value of the voltage across the primary winding. And again here 50 means it is the RMS value of voltage across the secondary winding. Strictly speaking, one end of the secondary winding to center tap, RMS value. So here VRMS secondary, it is given as 50, which is also given by peak amplitude by root 2. So which implies what is our peak amplitude? 50 root 2 volts. So now coming to our VDC, 2 into 50 root 2 by pi is equal to 100 root 2 by pi. So option A is correct. It's a simple one. Next question. In a full wave rectifier using two ideal diodes, VDC and VM are the DC and peak values of the voltage respectively across the resistive load, which is just similar to the previous case. Center tapped full wave rectifier, they are taking. Okay, ideal diode and ideal transformer. Okay, if PIV is the peak inverse voltage of the diode, then the appropriate relationships of this rectifier are. Okay, they are asking what about DC and peak inverse, VDC and peak inverse voltage, right? So we know VDC is equal to 2 into peak amplitude of the input voltage by pi into RL by RS plus RF plus RL. Again, ideal diodes means RF is 0, ideal transformer RS is 0. So I can cancel R and RL. It is 2 into V peak by pi. We can take it so. Okay, VDC is equal to. But what is V peak? Okay, keep it aside. And again, what about output peak amplitude, whose value is given as Vm? That's why I'm writing it. So V output peak is equal to V secondary peak or V peak. I can write it like V peak by RS plus RF plus RL multiplied with RL, and whose value is given by Vm is the peak value of the voltage across the resistive load. So it is denoted by Vm. What to do? This is the notation they are following. Okay, so here ideal diode RF, ideal transformer RS, both are zeros. So RL and RL cancel. So V output peak is equal to input peak, which is equal to Vm. Okay, so output peak amplitude and input peak amplitude will be same. I need not write this many steps, it's just implied. once ideal diode and ideal transformer are right, if you consider the case of ideal diodes and ideal transformer, automatically input peak amplitude is equal to output peak amplitude. That's it. So output peak amplitude is given as Vm, which is of course equal to input peak amplitude. If that is the case, I can write here VDC is equal to, in this 2 into V peak means it is Vm by pi. VDC value we have got. Next, what about peak inverse voltage? Peak inverse voltage is, it is 2 times peak amplitude of the input voltage. So its value is Vm. Okay, so which is correct? Option C. VDC is equal to 2 Vm by pi and peak inverse voltage is 2 Vm. That's it. The ripple factor in case of a full wave rectifier is, in case of full wave rectifier, ripple factor is 0.48. Option C. In a center-tapped full wave rectifier, 100 volts is the peak voltage between center tap and one end of the secondary winding. Okay, what is its maximum voltage across reverse biased diode? Peak voltage. We are well aware the notation and all. I need not write this much because we have done a lot of right, we have gone through a lot of discussions. So it is one end of the secondary winding and this is also one end of the secondary winding we are taking. It is like something like Vm sine theta I wrote it. And what about its peak amplitude Vm? It's given as 100 volts. That's what. Vm 100 volts is the peak voltage between center tap and one end of the secondary winding. Anyway, here one end of the secondary winding and it is center tap. And the peak amplitude in this example is 100 volts. And what about peak inverse voltage? According to this notation, PIV is equal to 2 times Vm, that is 2 into 100, 200 volts. Option A is correct. The circuit shown below is the Thevenin's equivalent circuit of a center-tapped full wave rectifier with diode forward resistance RF is equal to 100 ohms. The transformer secondary coil resistance RS is equal to 30 ohms. Peak input voltage from one end of the secondary winding to the center tap is Vm is equal to 10 volts. What are the values of V and RO respectively? Okay. The Thevenin's equivalent circuit it is given. So what can we write for this V? Or it is just nothing but V Thevenin's, it is equal to 2 into peak amplitude of input voltage by pi. It is 2 into, what is the peak amplitude here? It is 10 by pi, 20 by pi, it is 6.36 volts. We have got. And what about RO? RO is just nothing but R Thevenin's. It is nothing but RS plus RF. That's what we can write according to the notation we have followed. But here, what they mentioned, the transformer secondary coil resistance. Transformer secondary coil resistance means it's not like the resistance from one end of the secondary winding to center tap. It is the total resistance, right? What is the total resistance looking into this? That is taken as RS, whose value is 30 ohms. But our notation, the resistance between these two terminals, we took it as RS. Now it should be RS by 2 and the resistance between these two terminals is RS by 2 whose value is 15 ohms. Then what about R Thevenin's? This is right RS if and only if the voltage between one end of the winding to center tap is taken as RS. But in the problem, the voltage across the secondary winding is taken as RS whose value is 30. Then one end of the secondary winding to center tap means it should be RS by 2. It is 15 plus RF is equal to 100. It is 115 ohms. So option C is correct. We should be very careful here. We have practice of writing it like R Thevenin's is equal to RS plus RF and RS is given as 30. But the RS, what is their notation they are following means it is the resistance across the secondary winding, complete winding. not the resistance between one end of the secondary winding to center tap. That's where the students should be very much careful. A full wave rectifier uses two diodes. The internal resistance of each diode is 20 ohms. The transformer RMS secondary voltage from center tap of each end of secondary is 50 volts and the load resistance is 90 ohms. Mean load current will be, okay, mean load current means IDC. It is equal to 2 into Im by pi. 2 into Im by pi. It is further written like 2 by pi into Im is Vm or V input peak amplitude by Rs plus Rf plus Rn. Okay. Then here they have not mentioned anything about the transformer, so Rs is 0. Rf value, it is 20 ohms and RL value 980 ohms. Okay, this is also fine. And what about the peak amplitude of the input voltage? They mentioned RMS secondary voltage from center tap to each end of the secondary. So means they have given RMS value across the secondary winding. It is 50. It is just nothing but V peak by root 2. So V peak is equal to 50 root 2 volts. Now coming to this, it is 2 by pi into 50 root 2 divided by RF is 20 and RL is 980. So how much do we get? Root 2 by 0.1 pi. If you calculate it, you get 45 milliamperes approximately. Option C is correct. Simple formula substitution. A full wave rectifier with a center tap transformer supplies a DC current of 100 milliamperes to a load resistance of R is equal to 20 ohms. The secondary resistance of the transformer is 1 ohm and each diode has a forward resistance of 0.5 ohms. The voltage regulation is, okay, see here they have given the resistance across the secondary windings. This total resistance is given as 1 ohm, means this is Rs and this is Rs for us. So as the total resistance is 2 Rs now, right? Total resistance means between these two terminals. 2 Rs is 1, so Rs will be equal to 0.5 ohms. And the percentage regulation is equal to Rs plus Rf by R. R in the sense, instead of RL, I am writing R into 100. It is 0.5 plus 0.5 by 20 into 100. It is 5%. Option B is correct. Nothing to worry about the DC current given. IDC is 1 milliampere. Right? Nothing to worry about it. What do we do? Percentage regulation doesn't require the DC current. A full wave rectifier circuit is fed from a transformer having a center tapped secondary winding. The RMS voltage from either of the secondary to center tap is 30 volts. If the diode forward resistance is 2 ohms and that of secondary is 8 ohms for a load of 1 kilo ohm, the percentage regulation at full load is, and the efficiency of the rectification. Okay, again similar to the previous one only. If the diode forward resistance RF, right, is 2 ohms and that of half secondary is, this is RS is direct, half secondary they have mentioned. It's not like a secondary coil resistance. So this is what. Now the percentage regulation is equal to Rs plus Rf by RL into 100. Rs is 8 plus Rf is 2 by the load resistance is 1 kilo ohm into 100. It is 1%. Option A is correct. You see the difference between the previous one and this problem. Efficiency. The percentage efficiency given by 81.2 divided by 1 plus RS plus RF by RL. 81.2 divided by 1 plus 8 plus 2 by 1000. It is 81.2 by 1.01, slightly less than 81.2. And if you calculate it, you get it around 80.39%. It's a straightforward question. In a full wave rectifier, the secondary transformer output is 30 RMS value. Okay. The load and diode forward resistance are 100 ohms and 10 ohms respectively. The average voltage of load, what is V average, and rectification efficiency, the percentage regulation. Okay. So VDC, what is the formula for VDC? It is 2 into peak amplitude of the output by pi into RL by RS plus RF plus RL, average load voltage. So here, what about the peak amplitude of the secondary voltage? It is nothing but RMS value multiplied with 2. Okay, peak amplitude is 30 root 2 volts. 2 into 30 root 2 by pi into the load resistance is 100 ohms by, they have not mentioned anything about the transformer, so RS is 0 and RF is 10 ohms plus RL is equal to 100 ohms. If you calculate it, we get its value around 14.55 volts. We can, so 14 or 24 point. Okay, 24.55 volts. Option B is correct. And efficiency, the conversion efficiency, if we take it so, it is 81.2 by 1 plus RS plus RF by RL. 81.2 divided by 1 plus, anyway RS is 0, RF is equal to 10 by RL 100. So 812 divided by 11. It is coming to be around 73 point something. See, 11 sevens. So 7 figure you can see only here. So maybe 73.82%. Efficiency is also obtained. And the percentage regulation. Percentage regulation is equal to no load, okay, RS plus RF by RL into 100. RS is anyway 0, RF is equal to 10 by RL 100 into 100. Its value is equal to 10%. Option B is correct. Okay, that's it. Like this, we can do this problem. Next. In the figures A and B shown below, the transformers are identical and ideal except that the transformer in figure B is center-tapped. Assuming ideal diodes, the ratio of RMS root mean square voltage across the resistor R in figure A to that in figure B is, okay, it is half wave rectifier and it is full wave rectifier, center tapped full wave rectifier. And V primary is VO sin omega t in both the cases. And transformers are also identical. Okay, let me take V secondary as Vs sin omega t here. And here the turns ratio is same. And here the total voltage here, right, in this case, or in this case, the total secondary voltage is Vs sin omega t. But as it has some center tap, the voltage between one end of the secondary winding to center tap is Vs by 2 sin omega t, and other part is also Vs by 2 sin omega t. Done. Then what about the RMS value of half wave rectifier? Let me take it as VRMS1. It is just nothing but peak amplitude by pi. Sorry, 2. RMS, no, average means pi, we write it. So it is a Vs by 2, we can write. And RMS value of the second case, VRMS2. It is nothing but V peak by root 2. What is the peak amplitude here? It is nothing but Vs by 2. Right, Vs by into 1 by root 2. Then coming to the final answer, VRMS1 by VRMS2. So root 2 is the answer. Root 2 is to 1, we can write it. Root 2 is to 1. Option A is correct. Transformer is not changing. So primary voltage and secondary voltage across the secondary winding, they also do not change. The only thing is in figure B, we are using center tap, and hence the total voltage is splitting into two halves. And based on the voltage across one end of the secondary winding to center tap, we take RMS value as Vm by 2 instead of Vm by 2. That's the only difference. Based on that, the ratio will come. Question number 11. A full wave rectifier with a center tapped transformer supplies a DC current of 100 milliamperes to a load resistor of R is equal to 20 ohms. The secondary resistance of the transformer is 1 ohm, and each diode has a forward resistance of 0.5 ohms. What are the RMS values of signal voltage across each half of the secondary as well as the DC power supplied to the load? Okay, how do we do this? So here IDC is given, DC current 100 milliamperes, or I can even write 0.1 ampere. Okay, then we can write here VDC. Okay, VDC is equal to IDC into RL. It is 0.1 into load resistance. Instead of RL, let me write R. Just I am following the notation on the problem. It is into 20. It is equal to 2 volts. It is VDC across the load resistor. We are well aware. Once you know VDC, what they are asking? See, what are the RMS value of signal voltage across each half of the secondary, right? As well as the DC power supplied to the load. Okay, once you know these two DC power to supply to the load, we can write it. And PDC, it is equal to IDC square into RL or VDC into IDC, anything we can write it. So, right, 0.1 into 2, it's 0.2 watts. Option A might be our answer. Okay. Anyway, it is IDC square into R it is 0.01 into 20, it is 0.2 watts. So here from this, definitely option A might be correct because nowhere we have that zero point 0.2 watts. Anyway, let us have look at the calculations. Okay, so VRMS they are asking. VRMS secondary. What they are asking? Other part. RMS value of secondary voltage. Okay, how do we get it? First of all, what about V peak amplitude? V peak, it is equal to, or we know that from VDC, we know VDC is equal to 2 Vm or 2 into V peak by pi into RL by RS plus RF plus RL. Instead of RL, I am writing R because it is mentioned as R. And the secondary resistance of the transformer, it is 2 RS. It is 1 ohm. So RS will be 0.5 ohms. We know. So VDC is equal to 2. It is equal to 2 into peak amplitude of the input by pi into the load resistance is 20 by coil's internal resistance 0.5 and diode forward resistance is also 0.5 plus R, it is 20. Okay, so then this two and this two get cancelled and V output peak amplitude, it is equal to, so peak amplitude of the input voltage, it is equal to 21 by 20 pi. Okay, then once you know the peak amplitude, then VRMS secondary, RMS value of the secondary voltage is equal to peak amplitude by root 2. It is 21 pi by 20 root 2. If you calculate it, it comes to be around 2.33 volts. Okay, so definitely there might be some printing mistake here. It might be 2.33 volts, not 2233. That's it. This way we can do this. So it's also a simple one. We know, right, every point here. The data is given, just rearrangements. A full wave rectifier delivers DC power of 50 watts to a load resistor of 200 ohms. Then the AC ripple voltage across the load. AC ripple voltage across the load they are asking. Okay. DC power delivered to the load. So PDC is equal to IDC square into RL. It is given as 50 watts is equal to IDC square into RL is 200 ohms. So IDC is equal to 0.5 amperes. Straight away I am writing it. So 1 is equal to, or IDC square is equal to 1 by 4, or IDC is equal to 0.5 amperes. Okay, IDC we have got. Then from this, like similar problem, previous one only, right? VDC is equal to, or IDC is known and it is equal to 2 into Im by pi. So I can write here Im is equal to, or 1 point, I'll do one thing, 1 by 2 amperes. Im is equal to pi by 2 IDC pi by 2 into IDC. DC. Pi by 2 into what is IDC? 1 by 2 amperes. So it is Im is equal to pi by 4 amperes. Im value we have got. Then what about IRMS? RMS value of AC component I am writing. Because right, we have already gone through all these discussions. So to be frank, you see, I of t, it is just nothing but IAC plus IDC. And RMS value of this is IRMS, we say. And RMS value of AC component is IRMS dash. Okay. So now IRMS dash means RMS value of AC component. What it is? Right, IRMS means Im by root 2, we know that, and IRMS dash, it is equal to square root of IRMS square minus IDC square. It is equal to IRMS dash is equal to square root of IRMS square minus IDC square. It is equal to IRMS, it is Im by root 2 whole square minus IDC whole square. Okay, so it is further written like Im is equal to pi by 4. So it is pi square by 8 into 2 minus IDC. IDC value is already we calculated it. It is 1 by 2 means 1 by 4 IDC whole square. No, it's pi by 4. It's not 8. It's 16. Pi square by 32 minus 1 by 4. We can write so. Okay. And if you calculate its value, it is found to be, so 1 by 4. Pi square is approximately equal to 10. IDC, right. So I'm writing it approximately. It is 10 by 32 minus 1 by 4. Okay. 2 first 2 16ths. Square root of 5 minus 4 by 16. 1 by 16. 1 by 4 amperes. Okay. RMS value of AC component. I RMS dash. Then RMS value of AC component across RL. That's what they're asking. AC ripple component voltage across RL. So AC ripple component across load, it is nothing but IRMS dash into RL. Across load means load resistance. We can take it. It is nothing but 1 by 4 into RL. It is 200. So it is 50 volts. So option B is correct. That's it. Okay. So from the given data, what I did, I calculated IDC. From IDC, I calculated IM. And once I know the value of IM, RMS of value of AC component can be comfortably calculated. Once I get it, current value I know. Voltage means that current multiplied with RL. That's it. Yes. The waveform shown in solid line is obtained by clipping a full wave rectifier sinusoid shown dashed. the ratio of RMS value of the full wave rectified waveform to the RMS value of the clipped waveform is rounded up to 2 decimal places. Okay, how do we do this? So dotted line, it is like right, full wave rectifier output, and RMS value of full wave rectifier means peak amplitude by root 2. Dotted line I'm taking. So RMS value of full wave rectifier output. Let me write it as VRMS1. It is just nothing but peak amplitude by root 2. So full wave rectified output, it has a peak amplitude of Vm. So it is Vm by root 2. First part is ratio of this one to RMS value of the second waveform. Second waveform, we have to define it first of all. How do we define this second waveform? 0 to pi by 4, it is looking like Vm sine theta. And pi by 4 to 3 pi by 4, it is constant 0.707 Vm, means Vm by root 2. Again from 3 pi by 4 to pi, it is Vm sine theta over one cycle. That is the definition. Okay. So let me write that as V of t. V of t is equal to Vm sine theta over the limits 0 to pi by 4 is equal to Vm by root 2 over the interval pi by 4 to 3 pi by 4. Again it is Vm sine theta from 3 pi by 4 to pi. That's it. Once you define the signal, then automatically we can write its RMS value. Let me take it as VRMS2. It is equal to 1 by t integral 0 to t v square of t dt. Or I can further write like it is 1 by period is pi over one cycle. I have defined it 0 to pi. It is one cycle. 0 to pi by 4 Vm square sine square theta d theta plus pi by 4 to 3 pi by 4 Vm by root 2 whole square d theta plus 3 pi by 4 to pi again Vm square sine square theta d theta. Further 1 by pi into Vm square can be taken out of this integration Vm square, and sine square theta can be written as 1 minus cos 2 theta by 2. 0 to pi by 4 1 minus cos 2 theta by 2 d theta plus again Vm square by 2 into integral 1 d theta, it is theta over the limits pi by 4 to 3 pi by 4 plus again here I can take Vm square out of the integration 3 pi by 4 to pi sine square theta, it is 1 minus cos 2 theta by 2 d theta. Further, actually everywhere we can take Vm square by 2 outside, that is Vm square by 2 pi into it is theta minus sine 2 theta by 2 over the limits 0 to pi by 4 plus it is 3 pi by 4 minus pi by 4, the second one. And coming to the third one, again theta minus sine 2 theta by 2 over the limits 3 pi by 4 to pi. Then further Vm square by 2 pi into first one pi by 4 minus 0 minus sine 2 pi by 4 minus sine 0 by 2, the second portion, plus 3 pi minus pi, it is 2 pi by 2, that is pi by 2, plus again it is pi minus 3 pi by 4 minus of sine 2 pi minus sine 2 into 3 pi by 4 whole thing by 2. That's it. So further what we can write here, let me change the color. Sine pi by 2, it is 1, sine 0 is 0. Again sine 2 pi, it is 0, 2 2's. Sine 3 pi by 2, it is minus 1, minus of minus plus 1. Again it is becoming. Okay. So let me do the calculations in the next step. Otherwise, here sine pi by 2, if you take this, its value is 1. And here also this value, right, this whole value, sine 3 pi by 2 is minus 1, and that has already minus sign. So automatically it becomes plus 1. So Vm square by 2 pi, first one you get here pi by 4, next one 1 by 2, pi by 4 minus 1 by 2, plus pi by 2, again pi minus 3 pi by 4, it is again equal to pi by 4, the last one minus 1 by 2. So what we can see here is Vm square by 2 pi under root pi by 4 plus pi by 4, pi by 2 plus pi by 2, it is pi, and minus 1 by 2 minus 1 by 2, it is minus 1. Or it is Vm by root 2 into square root of pi minus 1 by pi. Then RMS value of the first case to the RMS value of second case, the ratio. It is first case, it is simply Vm by root 2 by second case Vm by root 2 into square root of pi minus 1 by pi. It is, these two will cancel. It is square root of pi by pi minus 1. If you solve it further, it comes to be 1.21. It's a answer is coinciding with that of ripple factor of half wave rectifier. Anyway, final answer is yes. Okay, that's it. This is how we can do this problem. See, it involves some mathematics, but nothing is there in this, right? Just some waveform is given. We are finding the RMS value of this particular waveform, nothing else. Once you know the RMS value of center tapped full wave rectifier and the particular waveform, clipped waveform given, the ratio only. It's just it is involved some bit of mathematical calculations. That's it. This is how the questions have been asked.